All right, please tell me. So this is a slideshow, but I don't actually run it in the slideshow viewer itself because when I do that, I lose the ability to have a mouse to point things out to. So it doesn't look quite as nice as actually I would like it to, but you guys get the idea here. But what you basically should be looking at, something right here, is hopefully I just want to make sure everybody can see. It's a picture of a computer
You
with
didn't share your screen, I don't think.
Yep, see, that's where exactly. Thank you, whoever brought that up. All right, now you should be looking at presentation. There's a sort of a laptop computer with two scales on either side of it, right and left. Can everybody see that part? Anybody not see that part? All right, so in this drawing situation, what I want you to sort of like, this is my attempt at bad animation, but nonetheless, it works. What this is it's a computer screen right here. There is an electronic scale on the left side, an electronic scale on the right side, and there's a single 1 ounce weight sitting on the left part right here. And so that's my setup right here. Does that make sense to everybody what my sort of setup is? We good on that part? Okay. So I have just added a 1 ounce weight to the right side of this scale. And so how much weight does the computer think I have actually added? Does the computer say to itself, okay, he just added the same amount of weight that we started with on the left-hand side? What do you think? Wow, you guys are already suspicious of me. That doesn't usually happen until the 5th or the 6th week. So again, the question is, how much weight does the computer sense that I have added on the right-hand side? And the answer to that is 1 ounce. That is correct. The computer understands that what I added over here was exactly the same weight that I started with on the other side. Pretty simple, right? Again, there's not that much trick in this. I add another 1 ounce. Now, the computer knows that there's more weight on this side. That's not what the question is. The question is going to be, does the computer think that what I added here was the same weight that we started with in the beginning? Does that make sense? It knows there's more weight on this side. That's not what the question is. The question is what I added here the same as what I started with on this side over here? And yes, the computer knows that that's exactly what happened. I'm going to do it again. I've added another ounce weight here. Now, again, the computer knows there's more weight on this side. That is not what this question is. The question is the weight that I added here the same as that we started with in the beginning? Does the computer understand that every time I'm adding an ounce, it's like, oh yeah, he's just added the same amount that we started with. I know things are getting heavier on this one side, but every addition that he's doing here is the same amount of weight that we actually started with. And again, the computer actually does know that. So, and this keeps going on. And every single time the computer knows that, yes. So again, even though there's now considerably more weight on the right-hand side, every one of those additions was the same increment of weight that we started with on the left-hand side. Are we good on this? Everybody comfortable with this? All right. Oops, sorry, wrong way. This is what we call a linear scale. And you can see that in a linear scale, in this case, we're going to do the one on the top. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And what you see about or it doesn't have to be single digits. It can be 100, 200, 300, 400, 500, 600. Those are all linear scales. What you need to know about a linear scale is that the difference in any two is the same as any other two. So again, the difference between 2 and 3 is exactly the same as the difference between 9 and 10. It's just 1. Does this make sense to everyone? That's what a linear scale is. Every one of these steps is exactly the same increment. To go from 4 to 5 is the same as going from 1 to 2, or 6 to 7, or 8 to 9. It's all the same. Linear scale. The same thing down here. It doesn't have to be only one single digits. It can be hundreds here. So the difference between 100 and 200 is exactly the same as 400 and 500. Every one of these steps is exactly the same. We good on this part? Okay. This is a picture of my wife, Debbie. It's not really a picture of my wife, Debbie, but I wanted to name her something, and my wife's actually name really is Debbie. So, you know, it's just sort of giving it a, you know, a face, a name, familiarity, someone you could care about, someone that you could love, someone that you know, anyway. She's wearing a mask, so she cannot see anything that's going on. The only sense that she can really judge here is her sense of sense of touch, right? How much weight? So we're going to do the same experiment here. I'm going to start. There's a 1 ounce weight that is in her left hand, and I am going to add a 1 ounce weight to her right hand. And the question that I've got for you is, how much weight does she sense that I have added? Does she feel like I have added 1 ounce? Does she feel like that the weight that I put down here is the same increment as the weight that is over here? What is your guess? Wow, you guys really are.
That she feels 2 ounces?
No, she knows that I'm just asking, is what she feels like she has in her left hand the same as in her right hand? When I actually added this weight on her right hand, did she think, okay, that's the same I had in my left hand? Does she feel that?
Oh yeah, probably.
And I would say probably too, right? So, and again, yes, indeed, that is correct. However, this is where things are going to get tricky. Now, instead of adding another weight, I'm going to add 2 ounces to her right side. And so again, the question is not, does she know that there's more weight on this side than this side? She does. The question is, does she feel like that these 2 ounces are the same as the original 1 ounce weight? In other words, does she feel like I've just doubled the weight on this side? Does she see these 2 ounces as being the same as the original 1 ounce of weight? What is your guess?
No.
Yes, she does. Her sense, when I put these 2 ounces of weight right here, is that yes, indeedy, he just added 1 ounce of weight to this. Her sense is that this weight has simply doubled, not in this case, tripled. That's what she senses. Hold that thought for just a second. Now I'm going to add 4 ounces to her right-hand side. Again, she knows that there's more weight over here on this side over here. However, my question is not that. My question is, does she believe that this 4 ounces of weight that I just added is the same as the original 1 ounce increment of weight that we started with? And the answer is yes, she does. She senses that this 4 ounces is exactly right now. She feels like, because again, she can't see, she feels like there's 3 ounces of weight in this hand, not the 1, 2, 3, 4, 5, 6, 7 ounces that there really is. And this continues to happen. Sorry. Here, 1, 2, 3, 4, 5, 6, 7, 8. I've added a half a pound right here. At this stage of the game, she feels like I have only added 1 more ounce. She sees all of this as being the same as the original weight. I know it gets confusing. Hang over, just stay with me for a little while. Once we get through all of this, we will stop and revisit. And if it hasn't made sense to you guys by then, we can talk about it and have other questions. This continues to go on infinitely. You'll notice what is happening here is every single time I'm actually doubling the content of what we just did before. I started with 1, I doubled it to 2, I doubled it to 4, I doubled it to 8, I've now doubled it to 16. What would be my next amount of weight? Would be 32 ounces. I would be putting 2 pounds on her, and she would feel like I have merely added 1 more ounce. This is a logarithmic scale. Again, this is the scariest word that I'll probably throw out to you guys the entire semester. It is a logarithmic scale. The scale is exponential. And an example of this would be, again, a doubling situation. This is exactly what we did here before. You start with 1, you double it and you get 2. You double it again, you get 4. You double it again, you get 8. You double it again, you get 16. You double it again, 32. Double it again, 64. Double it again, 128. The steps between these on like a linear scale are not equal. The difference between 64 and 128 is 64. The difference between 1 and 2 is 1. However, if you view this as a logarithmic scale, it appears that these are all the same in their distance between each other. So you think, well, number 1, that's impossible. And number 2, I've never seen anything like that in my life. Wrong. This is a linear scale. Sorry. This is a logarithmic scale. Do these things down here on the bottom look familiar to anybody? What are they?
Those are f-stops, but it's missing the 1.2.
Well, you can go down forever.
I'm kidding.
Yeah, it's also missing. Okay, so all right. Let's just see how good you are. I need everybody to turn their mic on, please, with me. And we're going to recite the f-stops. And I'm going to see just how far you guys, what you know and how far you can go. So let's start at F2. What's 1 stop down from that?
1.8.
8.
Down.
Oh, well, down. I'm sorry. 2.2.
It's right on the screen.
2.
2.8.
2.8. 1 stop. Is that a full
2.8.
stop?
Full stops.
Okay, so it'd be
Okay.
2. It'd be 2, 2.2, 2.5, and then 2.8. That'd be a full stop. I got you.
Not doing thirds of stops here. Full stops.
Gotcha.
All right, but everybody join in here. What's 1 step down from 2.8?
4.
4. Next stop.
5,
5.6.
6,
5,
Next.
6.
8. Next.
11,
F11.
Next, you can read it off this. 16.
16.
Next,
22.
22.
32. What's
32.
after that?
64,
No, that's it. 32 is
45.
it.
Oh, no.
64, right?
45 is after.
Oh,
32.
45.
What's after
45.
that?
64,
Yes, what's after that?
like 128.
8.
Nope, 90. What's after that?
Oh,
128. What's
There we
after
go.
that? 18.
Um,
What's after that?
256.
Yep, exactly. It just keeps on going like that. What is the relationship between f-stops? What is the difference in 2 and 2.8 in terms of the amount of light?
1 full stop.
And how much is that?
Double the light.
Double the light or having the light, correct?
Mhm.
If I go from 2 to 2.8, am I letting in more light or less light?
You were
Less-
letting in
Less
light.
light.
Right, so it's half the light, correct?
Mhm.
And then if I go
Yes.
from 2.8 to 4, it's half again. If I start on the other side, if I start at 32 and I go to F22, is it more or less light?
More light.
How much more?
Double.
Double.
Double. If I go to 16, how much more?
Double.
Double.
And if I go to 11, how much more?
Same.
Double.
Yes. However, if you were to shoot these on a single exposure and you looked at them, this would be a perfect step wedge of grays. You would see the same change between 2 and 2.8 as you see between 16 and 22. But the reality is the amount of light here is considerably different, just like it is in our other scale right here. If we go back, to this situation right here. Same thing, we're doubling the whole time right here. The difference that she senses in this amount of weight at the top is exactly the same as this, and as this, and as this, and as this. She sees those as being the same, and it is the same here in f-stops. So why does that matter? Where did f-stops come from? Who the fuck figured that out?
It was it has to do with the distance from the.
No, let's not go down that road. It has nothing to do
Okay.
with that. It's based on
Alright.
human vision. It's based on how your eyes see. Your eyes see logarithmically. They do not see linearly. They see logarithmically. Your weight perception, your feel is logarithmic. That's why you had to double those weights every time in Debbie's hands for her to sense that you had put the same amount of original 1 ounce weight on her to begin with. Your sense of taste is logarithmic. If you had take a cup of tea and you put in 1 sugar cube and you stir it in and you taste it and you say, okay, I can taste how sweet that is. And you want to add exactly the same amount of sweetness again, you do not add 1 sugar cube, you have to add 2 because your taste is logarithmic. You've now added 2 sugar cubes. You say, okay, I want to add the same amount of the original sugar cube again. You've got to add 4 to have the sense, to have your sense of taste register that you have added another one of the original single cubes of sugar taste. Does this make sense? And it just goes on. So the sugar cubes, you start with 1, the next version is 2, the next is 4, the next is 8, the next is 16. You get up, you have to add at the 5th step, 32 sugar cubes for your sense of taste to feel like you've added that 1 amount of original sweetness single sugar cube that we started with, because your sense of taste is logarithmic. Anybody in this room deal with sound at all? Do we have any sound people, music people, anybody in here for that? Anybody in here ever heard of decibels? Decibels is how you measure sound. Decibels are logarithmic. The difference in a decibel of 60 and 61 is a doubling of the sound. From 61 to 62 is another doubling of the sound because your hearing is logarithmic. All the senses of the human body are logarithmic. They are not linear. The reason that f-stops were built this way is that because this is how your eyes see. If you were to do a grayscale that was linear, your eyes would not see those steps as being even. The logarithmic scale, you do see them as being even. Does that make sense to everyone? Who have I lost? Okay. It's not just logarithmic in the sense of full f-stops. If you go old school and you look at any older shutter, any lens that is not, any basically shutter that's not electronic, a mechanical shutter, whatever, they had complete f-stops of shutter speeds as well. And you still see this in meters today. If you use a handheld meter, it will have full f-stops on it. And again, you see that this is a doubling. So again, or a doubling or a halving. If I go from a 15th of a second and I cut it in half, it's a 30th of a second. If I cut a 30th of a second in half, it's a 60th of a second. If I cut that in half, in reality, it should be 120th, but they change it to 125th because it's close enough and it makes the math easier. Again, 125th cut in half is a 250th. If I start down here at a 1,000th of a second and I want to double the time, I go to a 500th of a second. If I want to double it again, I go to 125th. Does this make sense to everybody what's going on here?
You just messed my head up for life, pointing out that it should be 1 over 1 over 120.
Oh, yeah. Well, there's another cheat too. When you cut this in half from a half of 115th, it really should be 1 over 7.5, and they do it 1 over an 8. So, but anyway, that's how these whole things work. This is our system of working with exposure. You guys have worked with this all along. Nobody had any trouble with this before. It just fucked with your head the minute I told you that this is how your senses actually operate and work. But this part becomes critical to everything that we are going to do in this class. This is your language. So right off the bat, I'm telling you, you need to memorize your f-stops. That is the language people use in the studio. Now, you don't need to get up to 128th of an f-stop, or you really don't need to get down to f.7. You can stay pretty much in the 1.4 to 32 range, and you should be pretty good. Maybe if you're working in view camera will actually get up to 45 or f64. Anybody in this group here ever heard of Edward Weston? Okay, list of everybody start your list right now. List of photographers you should be looking at. Edward Weston, one of the masters, right up there. Again, more old school U.S. masters, but the whole Ansel Adams, Minor White group, that whole group in there. Anyway, Edward Weston launched a thing called the F64 Club. Where do you think F64 came from? Exactly this. Because all of those guys were shooting 8x10 cameras. So the range that we're comfortable with working in here, f2 to f32, is for 35 millimeter. When you start getting up into larger format cameras, this is inadequate. F32 would be a middle range for an f-stop for an 8x10 camera. You get up into the 45, 64s, all of those guys shot at f64 because they were looking to have all of their stuff was really tack, serious depth of field, and that's where they would all work. We can't ever get to, there's not a lens made for a 35 millimeter system that's f64, but there sure is in, again, large format, 4x5, and if you can get even bigger than that. So does this make sense to everybody, what's going on here? This is our language and we need to exploit it, but there are implications from this that go further than what we are looking at right now. So this is the reason it exists. This is the reason your body evolved to be this way. So if you look at this graph, and again, I know this is seeming very math-centric right now. It's not meant to be that way. It's just meant to give you an idea of why the system is the way it is, why your body evolved the way it evolved was to be able to do this. If you take a look at the little blue bars that are sitting down here at the bottom, that is a linear scale. If you go from 1 to 2, it's exactly the same height increase as from 2 to 3, exactly the same as 3 to 4. The height increase from 7 to 8 is exactly the same as it is from 1 to 2. It's just even steps. For 8 steps here, you simply go up by 1 every single time. But look what happens in a logarithmic scale. You start at 1, then you double it to 2. That's actually the same as a linear scale, but then it doubles again to 4. Now we've done a serious jump. It jumps again to 8, then to 16 to 32. Look at in 8 steps, the range, the extended range of sensation that I'm actually able to perceive as a human being, because I work in a logarithmic scale, not a linear one. So let's put this in practical terms. You can go out, it was a really bright sunny day earlier today. You could go out on that really bright sunny day with the sun blaring down, whatever, and you could look at a car that was parked on the street. And if you looked, you would see that underneath that car, there was a black shadow that was coming. So the sun is beating down and there's a black shadow underneath that car. Your eyes can spot the detail in the highlight on top of the fender of the car, and also at the same time pick up the detail in the shadow that is underneath your car. Your eyes can do that at the same time because your eyes have this gigantic range of input that it can take because your eyes are logarithmic. Does that make sense to everyone? It's a way for your eyes to be able to see a range that would never be possible if your eyes were linear. That's why this exists. So photography simply aped onto it. It just said, okay, well, we're just going to do it the same way your eyeballs do it, and that'll make sense. Are we good on that part? All right. Are there questions about this? I told you in the beginning, this is kind of a tough one. We're not going to dwell on this a huge amount of time, but this has serious implications for us that we have got to get through, that we've got to embrace in this class, especially in a digital world. In a film world, even though film is designed this way. Film is logarithmic. Printing paper, if you go into the darkroom and you print, printing paper is logarithmic. It's what your eyes expect to see. That's why it was all designed that way. It's a miracle that the people who invented the very first film actually were able to chemically engineer it to be logarithmic. This is no easy feat. Okay. You can correct a linear thing to mimic a logarithmic thing. And that's important to us, because a lot of what we deal with in a digital world is linear, and we need to make it logarithmic. So this is the rub that we run into. Your camera, digital camera, is a linear device. That does not work for us. If you were to see a linear output, you would be shocked at what it really looks like. I'll show you, I'm going to show you pictures of what it actually really looks like. It doesn't look anything like you think it should, because your eyes are logarithmic, not linear. Your computer monitor, the screen that you're looking at right now, is linear. It's got to be adjusted to emulate a logarithmic scale so that you see it this way. So what happens is, in this scale right here, this move that is made like this, whatever, it's simply a curve that's put on to your computer screen. When you actually calibrate your computer screen, you actually set the curve for this to say, okay, I need this kind of correction here, because you need your monitor, which is linear, to mimic a logarithmic world so that it makes sense to your eyes. Don't worry. We're going to go through this over and over and over again. If you are struggling with this right now, hang in there. This will begin to make more sense. And as we continue down this road, it will continue to come up. And again, it will sort of set in. Are we good on this? So I'm just asking you to hang with me on this one. Okay. I'm going to jump out here for just a really quick second here and ask you guys, what's middle gray in photography? Anyone?
128.
That would be in Photoshop. I'm thinking more now in film. We'll start with film. Anybody in here ever heard of an 18% gray card?
That's for like checking color balance.
It can be for checking color balance, but 18% is middle gray. You guys can look it up. Actually, 18% is middle gray in film. Things have changed a little bit when it comes to digital. We'll talk about that in a second. But I'm just asking, so really there's people in here who have never heard that an 18% gray card, a 18% Kodak gray card is we've never heard of that part? I'll find one in a second. I'll show you one in a second. Anyway, 18%. Why isn't it 50%? I'm going to tell you why. So how many people in this room have heard of Ansel Adams? Okay, that's a good one. How many people in here have ever heard of the zone system? One person? Oh my God, your photo teachers, your foundation photo teachers should all just be lined up and whipped. I don't want to say shot, but they should be spanked. And we can all get in on the spanking. No, I didn't say that. So here's how it works. I'm going to jump out really quickly. I got to find another image that I want to show you really fast. So hang on just 1 second. All right, can you guys see a scale on my screen right now that says zone system?
Yep.
Okay, zone system. This was developed by Ansel Adams and Minor White. They were the first people to really sort of like quantify this. And what their initial hypothesis in all of this is that in a given image, a fully resolved, fully tonal range image, that there were 10 distinct zones. of tone. Now, again, we're dealing with black and white right here. So that's basically the premise that we're dealing with. And it was called the zone system. And so the way the zone system started out, if we take a look right here at zone 0, zone 0 was as black as a print could be. So you would take a printing piece of paper, you could set it out in the bright sunshine for a day and a half, develop it, and that was the blackest. They would call it a D-max, the maximum for the density of that paper. That's what it was. That is zone 0. You can take a look right here. Black, there is no texture or detail. As we get to zone number 1, we get to near black. There is still no detail, but you are beginning to distinguish some gradation. If you go to zone 2, again, it is a really dark gray. There's a possibility of slight texture. It may be there, it maybe isn't there. You know it's not quite zone 1, but you're beginning to distinguish some amount of detail, but it's maybe there, maybe not. Zone 3, this is the critical one. Zone 3 is full shadow detail. In a print, zone number 3 is shadow detail, and it is full detail. Zone number 4 is a medium dark gray. Again, I'm going to show you these. So it's these sort of colors up here at the top, although these are somewhat approximate, but nonetheless, it's zone 4 is medium dark gray foliage. It's the shadow side of Caucasian skin. Details are plainly visible. Zone 5 is considered middle gray. This is what every meter in the world measures. The meter in your cameras measure zone 5, middle gray. We'll talk about why that is in just a second. Anyway, that's what zone 5 is. It is medium gray. It's an 18% gray card. Kodak was very famous for producing 18% gray cards that you could do reflected meter readings off of, and they would indicate the proper exposure for you. It's, if you're shooting black and white, what you would get on a clear northern blue sky, excellent detail available to you. Zone 6 is, again, it's a rich mid-tone. It is the average of Caucasian skin on unfiltered black and white film. Zone 7. Zone 7 is a bright light gray, and it is the highest zone that still holds good detail. So again, it's full highlight detail at zone 7. Zone 8 then starts to get to lighter. And again, you really don't know that there's detail there. You have some sense of gradation. Zone 9 is almost white. And then zone 10 is paper white. Those are the 10 zones. And that's what Adams exploited when he would make all those amazing prints of the Sierra Nevadas. He said by his rule of thinking was you needed all 10 of these zones to be present in a black and white image to have it be a properly exposed and printed black and white image. Does this make sense to everyone? However, what he also said was the range of visible detail went from zone 3 to zone 7. That's a 5-stop range. We good on that part? 3 to 4 to 5 to 6 to 7, a 5-stop range. In film, you have a 5-stop range of available detail. It doesn't mean that it can't get lighter and darker, but it is where all of the detail has to reside. Is everybody good on that part? Okay, so hang on one second. We're going to get through this, guys, and trust me, this is the most theory-heavy class, and typically I don't do this one first because I know that some of you guys are going right now, I didn't sign up for this shit. I'm out of here. Hang with me. This really does matter. It really will come into play, and again, you'll be fine. I promise you that. I'm going to stop sharing for 1 second. And I'm going to go to my whiteboard really quickly. So please tell me if you can see the whiteboard right now. I can't see you guys, so I need a verbal. Can somebody tell me, can you see a whiteboard?
Not yet. It says he started screen sharing, so.
Can you see it now?
Oh, there we go. Yep.
Okay. It's weird. It stopped working on this screen yesterday, and now it's working here again. Okay, so we are going to talk about that 7 stops of range. So, I mean, the 5 stops of range for film. So I'm going to start over here. We're going to do this in percentages. I'm going to start over here at 100%. And then logarithmically, I'm going to go down one stop. What would one stop be less than 100%? How much is an f-stop in value?
That's a third stop.
Nope, those are the divisions in between. What is a
Okay.
full stop?
Full
Maybe
stop.
50?
Half.
50?
Exactly.
80.
Again, f-stops are doublings and halvings. So if I go down one stop less light, I get to 50%. I'm gonna try this with a tablet, guys, because that writing looks horrible. Not that this is gonna be any better. Oh, and not that that's gonna be on. What's my next stop down?
25.
25. What's my next stop down?
15. Oh, 12.
12 and a half. You guys can use a calculator. What's my next stop down? 6 1/4. What's my next stop down? 3 1/8.
Mm-hmm.
So what you have here, this is zone 3. Dark. You only get, this is light that's being reflected off of a print. 3 1/8% of the light is coming back to you. That is really dark. Up here, 100% of the light is being kicked back to you. This is zone 7. So this is zone 6, zone 5, wait, anyway, that's going to mislead you right here. So hang on, let me erase that part. So does this make sense what's going on here? This is 1 stop, 2 stops, 3 stops, 4 stops, 5 stops. This is the 5-stop range of film. Does this make sense to everyone? Again, I can't see you guys, so are we good? Are you still there?
Yes.
Yep.
Okay, hang on. I'm going to try to get your window back so I can at least see people sort of nodding.
Wait, I think I kind of am a little confused. So if there are 10 zones, but only
Yes.
5 of these in the film, then like where do the other ones come from?
The other ones are beyond the range of detail. So even though they
Oh,
play into it, they don't mean anything to us because the only thing they appear to us on both of those sides is either white or black.
okay, cool.
So this is film. So let me ask you this. This is going to be the most math intense I'm going to go for you right here. 5 stops range here. What is half of 5?
2.5.
2.5.
Exactly, 2.5, right? So if I start here again, let me grab my drawing part. If I go here, 1 stop, 2 stops, 2.5 right here. What is exactly halfway between 12 and 25?
18.
18. This is why 18% gray is middle gray, because it's the middle of a logarithmic scale, not a linear one. If we were in a linear one and we had 1 to 100 right here, 50 would be the middle part of it. But sorry, that is nowhere near the middle, is it? 50 would be the middle part of this right in here. But in a logarithmic scale, 50 is only 1 stop down. So you can see the logarithmic scale gives us much greater perception of tone than a linear scale would. Does this make sense?
I have a question.
Shoot.
So you said it was zones 3 through 7, right?
3, yeah. So it's
So that
you have to count those. You don't subtract 3 from 7. It's zone 3, 4, 5, 6, 7. 5 stops.
oh, but then how come if you start from 3 1/8, you go 3, 4, 5, 6, 7, it stops at 50?
No. If I start at 3.8, 1
Yeah.
stop, I would double. It'll be 6.6 1/4. Then it doubles again, 12, right? Doubles
Mhm.
again. Okay, we need to look at another thing here really quickly, just so that you guys understand this doubling and why there's so much difference between, again, the difference between 3 1/8 and 6 1/4 is only 3 1/8. The difference between 50 and 100 is 50. But we see the jump from here to here as being identical as the jump from here to here. Okay, so we're going to do this one more time. Not one more time. We'll do this more than you guys probably are going to like, but nonetheless, this is critical. We're going to get through a little bit more of this. We're going to take a break and come back and finish this up. We're not going to just soldier on this. So we're going to do f-stops starting at F32 and go the other direction. So I'm going to start here, F32. What is one stop open?
22.
22. What's one stop open from that?
16.
Yep. What's one stop open from that?
11.
And one open from that?
I want to say 8.
Sounds like you're on a game show, Zach.
Right. Well, I thought it was 7-1 and I couldn't decide.
Alex, I'm going to take 8 for $50. One stop open from this.
5, 6.
One open from this.
4.
One open from this.
2.8.
One open from that.
2.
2.
I'm going to leave this scale as it is right now, just so that you guys, so it doesn't really work this way. This is pretty much just coincidence, but I'm going to throw this out to you anyway, just to help you, give you little tricks to start getting this whole idea of memorizing. It's the only thing I'm going to ask you to memorize in this class. I don't really believe in memory, in rote memory like that. My memory is horrible. I'm not that person. I don't know what the capital of Idaho is, and I never will. For me, if I can understand a system logically, then I don't need to remember things. I understand the process. That makes sense to me. I don't have to memorize some random set of numbers. You got to memorize this random set of numbers. I apologize. It just is what it is. However, there's a trick. If you take F2 right here and you double it, what do you get? The number. 2 times 2 is 4. If you double 4, you actually get 8. If you double 8, you get 16. So every other one for a while, actually, this system actually works. You can remember the whole f-stops. It sort of works on the other ones. If you do 2.8 and you double it, you do get 5.6. If you double this, really you get an 11.2, but they round it down to 11. But then it works from this point on. 11 doubled is 22. Then you double this, you go to 45, again, close, not quite. So it's just kind of again, and this is all coincidence. This has got nothing to do with doubling and having of f-stops. This is just a fluke that it actually works this way. Make sense? Okay. I'm going to start here at F32, and I've got 1 photon of light. I'm just going to put a 1 down here. 1 photon of light actually can hit my sensor. Does that make sense? I'm just trying to come up with a unit of light. You could call it anything. You could call it a photon. You could call it an EV. You could call it whatever. I'm just going to pick photon just to give you some amount of light. Does that make sense to everyone, what we're just going for here? So if 1 photon of light actually hits my sensor at 32, how many photons will hit it at 22? Is F22 is moving from 32 to 22 more light or less light?
More light.
Exactly. I'm opening up. How much more light?
Was it double we talked about?
It doubles, right? So it would be 2 photons right here. Does this make sense to everyone? If I go from 22 to 16, more light or less light?
More.
More.
How much more?
Double.
Double. So how many photons?
4.
Or, yeah.
Exactly. If I go now from 16 to 11, more light or less light?
More.
How much more?
Double.
How many photons?
8.
If I go down to F8 now, how many photons? F5, how many photons?
32.
F4, how many photons? F28, 2.8, how many photons?
128.
F2, how many photons?
256.
Yep. So this is the logarithmic scale. The way we perceive it, the change in a grayscale from 32 to 22 is exactly the same as 4 to 2.8. Every one of these steps seems perfectly even and the same amount. But look at the different in the terms of photons. There's the jump from 32 to 22, I've added 1 photon. But the jump from 2.8 to F2, which I perceive as being the same as the jump between 32 and 22, it's 128 photons. And this goes right back to Debbie and this setup right here. She believes that this entire amount of weight that we're added here is actually only 1 ounce, equal to this part right here. Are we good on this? Okay. Let's take a break right now. Everybody stand up, shake it out. I'm going to say it's, let's just call it 3 o'clock. Let's do a hard 15-minute. We'll come back at 1:15. We're going to jump in on the rest of this. Believe it or not, this actually gets put into practice. We're actually going to use this. This is going to define a set of parameters for us, for you specifically as assistant or a digital tech that is critical for how you approach shooting. So stay with me on this one and I'll see you guys in 15 minutes.
Mercer, can I talk to you really quick?
Of course. Hang on 1 second. Let me just stop the recording. So let me get a recording going again. Let me share my screen again. Okay, I want to just come back to what we were looking at earlier. Again, this is the 5-stop logarithmic responsive film. We start at 100%, we go to 50% to 25 to 12.5 to 6.25 to 3.4. I mean, that's just where we go down. In the middle is 18% gray. When digital came about, digital extended that range, and the way digital extended it, it's not really so much the capturing medium as much as it is the print medium. Most of you, all of you guys, do all of you guys print? Do you print any of your work? Most of you, some of you, anybody not print any work, you electronic only? If you're electronic only, this extends anyway, it applies to that as well. But what they did with inkjet paper specifically was they added what are called optical brighteners to it. So there's a coating in all inkjet printing paper, and there are optical brighteners in it, things that actually make the paper seem brighter. They also developed really dense inks. Epson and Canon and those people developed much. So what ended up happening is they extended that 5-stop range to an extra 6th stop. So they picked up, because the optical brighteners, they got a 1/2 stop more highlight detail, and for the density of the inks, they actually got a 1/2 stop more shadow detail. So what happens in those systems is that instead of 18 being a middle gray, it's now 12. So again, what ends up happening is that you go from 100%, you drop it down to, again here, this is the actual ones, but basically 50%, 25%, 12%, 6. And again, it's a 6-stop range now. 1/2 of 6 is 3. And so 12% is middle gray for digital. And the reason I bring this up is that if you use handheld light meters, older light meters, specifically Minolta meters and Konica meters, are based on a middle gray of 18%. Newer meters, specifically Sekonic, are based on 12% as middle gray. And you need to know the difference in those two, because as we get deeper in this class, we will actually use meters to establish specific tones for us. And if you are using the older version, and you think that it's the older version, which is an 18% middle gray, and you think it's actually, and you're basing it or putting it into a system of 12% middle gray, you'll be a 1/2 stop off. So that's basically the long and the short of it. But that actually gets you familiar with this whole idea of percentages as f-stops and as a range of tone. Is everybody comfortable with that part? Okay. So here is the problem, and this is a huge problem for us. It wasn't in the days of film, but in digital, this all changed. In the days of film, film was logarithmic, your eyes are logarithmic, and printing paper was logarithmic. So everybody was on the same scale. It didn't matter. But in digital, what happened is the digital cameras are linear, monitors are linear, and our eyes are still logarithmic. So we have got to deal with that shift. And that shift has very profound implications that we've got to embrace, that you need to be aware of, because those implications can cause gigantic hits in the quality of your work. And that's what we're going to look at right now. So that's all that this screen right here was meant to say. Your eyes logarithmic, your digital devices are linear. Believe it or not, this is what a linear raw capture looks like. Because it is linear, it has not been made logarithmic yet. It's extremely dark. You can see, and this is a normal exposure. This is not an underexposed file. It's very difficult to actually see a raw file that has not been corrected. If anybody's interested, I've actually given you a piece of software that will allow you to see the un-gamma corrected version of your capture, but they are all oppressively dark, because it is a linear capture. You can see that the histogram, all of the tone, everything is down here in the shadows. However, when you correct this using software, either Capture One, Camera Raw, Lightroom, Bibble, DxO, any processor, it applies that same curve, the one that I showed you earlier when we were way back here looking at this. This move right here is what's happening right here. There is a curve that changes that linear capture to a logarithmic one, and we see a full-scale toned image right now. Does this make sense to everyone what's going on? Are there questions about any of this? All right. So this is basically what's happening right here when we talk about this. This is a linear capture, and you can see that there is a really black tone here. These steps are not even. You can see that this is not a normal grayscale ramp. This is a linear capture. This, sorry, hang on, is one that's been adjusted to be viewed logarithmically. And so you can see it looks like this is an even step. To go from here to here is the same as from here to here and here to here and here to here and here to here. They're all, it's an even step wedge. If I pulled these little white lines out, this would simply look like a gradient going from black to white. That is not the case in a linear capture that looks like this. If I were to pull these lines out, you would see that there's a very small dark area and a gigantic light area. Does this make sense to everyone, what's going on? Okay, this is the last part of the math, and this is a tough one, but this is really important. And it's the foundation of why we've spent all of this time talking about this shit. And it's this right here. In a linear capture, what we need to talk about is the amount of data, the information that exists in that capture. How many of you people, let me just ask you really quickly, if you wanted a really dark and moody image, how many of you would make a really dark and moody capture?
I would just expose for the correct exposure.
Well, let's say you want a really dark, moody image. Would you make your exposure dark and moody? Yeah, that would be your natural inclination, right? And then in the days of film, that was actually true. That is not the case in digital, and there are serious consequences about that. So, bit depth. How many of you people can explain to me or actually know what bit depth is? We talk about it all the time. 8-bit image, 16-bit image. We talk about it, but do you know what it really means or what it really does or what it is?
It has.
Ain't it like the pixels in the I don't know if that's the right term. The pixels in the picture, how many pixels in there?
It's not how many pictures, no, that would be resolution.
Oh.
I think it has to do with the color.
It has to do with the number of tones or the number of colors available to us. That's what bit depth really is. Okay, so I'm going to jump out and show you another screen really quickly. Hang on one second, just so that you understand. Bit depth, this matters to you. You need to know this as well. So this is the quickest way I can explain it to you, and then we'll jump back and finish up the whole exposure part. This is, bit depth is all based on what they call a binary system. And a binary system is a very simple thing. It's just like a light switch. So in this illustration right here, you can see there is one light switch, and there's only two possible scenarios. The light is either on or off. Does that make sense to everybody, what you're looking at right here? The only two options, binary, two, on or off. If I add another switch to this, there are now four possibilities that we have available to us. They can both be off, they can both be on, or the one on the left is off and the one on the right's on, or the one on the left is on and the one on the right's off. These are the only possibilities that we have here. Does that make sense to everyone? Next one down, we add another switch. It's a doubling again. Sounding familiar? So again, they can all three be off, they can all three be on, or all these combinations in the middle. But every time I add another switch, I double the possibilities for me. Now, computers are actually made up of transistors, and transistors are nothing more than switches. If the switch is on, a computer will read the number as 1. That's the only numbers computers have, are zeros and ones, zeros and ones. That's all they have. If the computer is on, switch is on, you have a 1. If the switch is off, you have a 0, just like the light being on and off. If we add another switch to it, we have 4 possibilities, just like the lights. If we add another switch, we have 8 possibilities, just like the lights. That's computerese. We don't deal in computerese. What we deal with is photographs. So in photographs, some very smart people at Apple actually realized that you could assign those numbers for tones. So in this case, if the switch is on, you have white. If the switch is off, you have black. This is a 1-bit image. You have 2 possibilities. That's it, black or white. If we add another switch, you still keep black and white, but you get 2 shades of gray that are in the middle. This is a 2-bit image. There are 4 possible grays. If we go to the next, 3-bit image has 8 possible grays in it, and on and on and on. Does this make sense to everyone? Okay. In the real world, this is what a 1-bit image looks like. You have black and white. That's it. Very posterized. If we go to a 2-bit image, we still keep black and white, but we get 2 shades of gray. We get a very light gray and a very dark gray. That's basically what we've added to it. Still very posterized. If we go to a 4-bit image, we have 16 tones of gray, and you'll notice that every one of these, let me go back, every one of these along the bottom is the gray ramp for this as well. So you can see black and white. If I go to the 4-bit, I've got white, I've got black, the 2 shades of gray. If I go to a 16-bit, I'm starting to develop this gray scale, this ramp right here. But you'll notice at a 4-bit image, there's still very distinct jumps between these tones of gray. And the resulting same thing happens in the image. This is not what we would call continuous tone. If we go one more to an 8-bit image, you'll notice that the gray ramp at the bottom seems continuous tone. In truth, it's really not. There's 256 tones that are down there, but they're so close to one another, you don't see the gaps in between them. Does this make sense to everyone? This is why we deal with 8-bit images in Photoshop. This is why most cameras capture in at least 8-bit. It is not that it was some magical number. It's just that a bunch of people sat down when they were developing digital and looked at a bunch of prints and said, how many tones do you really need how many do you really need to give the illusion of continuous tone? And 8 bits was the minimum, and that's where it came from. Does that make sense to everyone? You can keep going on. I'm not going to show you this in color. I'm going to actually go back to our guy right here. So your typical camera, the how many of you guys are, I need to ask this. How many Canon people do we have? How many Nikon people do we have? How many Sony people? Do we have any Sony at all? No, that's fine. It doesn't matter, whatever. So depending on the age of your camera, it actually captures in a very specific bit depth. You can look it up. Most cameras, older series cameras, like a Canon 5D Mark II or a 5D Mark I, is probably capturing in 12-bit. And so what that means is that, again, you just do 2 times 2 times 2 times 2 times 2. If you do 9, 10, 11, 12. If you get up to a 12-bit capture in an older Canon camera, you have, if you're doing it in grayscale alone, we would talk about over 4,096 tones. So instead of the 256 that we had in 8-bit, which typically what we work with in Photoshop, or even 16-bit, this would actually be a 12-bit, 4,000 tones is basically what it's actually capturing. However, that is also translates into the data that is captured. And this is where the rub comes in. If you look at my screen right now, you can see this is based on a 12-bit image. There are 4,096 possible levels of gray that run along here. However, this is a linear distribution, not a logarithmic one. And as a consequence of that, when we put a logarithmic scale on this, what you see happens is this. The top one stop of your image, this is the brightest one stop, contains half of the data of your file. A full 50% of the data of your file is in the top brightest stop. Does that make sense to everyone? In the next stop is the another half of your data. So in the top 2 stops of your exposure, 3/4 of the data exists of your file. So going back to my question, do you make an image that you want to be dark? Do you expose it and make it dark? Well, if you throw away the first stop of your exposure, the brightest stop of your exposure, you've thrown away half of your data. If you then throw away the next stop to make your image all dark and moody, you throw away another half of your data. 75% of the potential data of your image sits in the top 2 stops. And if you underexpose, that data is not there, and your image is based on very little data, it's really noisy and shitty as it can possibly be. And your work is noisy and shitty as it can possibly be because you don't understand that in digital, it's not about exposure, it is about collecting data. You want to collect the most amount of data that you can possibly get to then process into a really dark, moody image. You want a fully exposed, maxed data, rich data set in your exposure that then you can do anything you want to with it in post. You can make it dark, you can make it light, you can make it moody, you can make it really high key, you can do all of that. You don't care about what the end game is. You care about getting the maximum amount of data that you can. And the deck is stacked against you. How many people in this room use the meter in their camera to make an exposure? Well, what do the rest of you guys do? Guess? All of you fucking use the meter in your camera. You point your camera at something, you dial it so the little thing is in the middle, or the little light goes on, or the little green thing blinks, or whatever, and you punch the fucking button, and you have been lied to. There is not a sensor that exists, I don't care whose sensor you're using, that the company has been honest with you about what the ISO of that sensor will really do. How many of you look at the little histogram on the back of your camera? Ooh, I can see my little histogram. How many of you put on the little highlight blinking warning thing that says, warning, warning, you're overexposing your file, you're overexposing your file? Do any of you guys use that shit? Well, stop, because it's lying to you. What you are looking at is a histogram or a warning of a badly processed JPEG in your camera. It's not what your raw data is at all. All of those things are forcing you to underexpose. They're all saying, you're going to clip this, you're going to clip this. We need you to underexpose, underexpose, underexpose. You get right into this situation right here. You underexpose by a full stop. You've thrown half of your data away. Half of the data that could make your file you have pitched. Try walking into some studio and say, hi, I'm here and I'm willing to I'm ready to set up and I'm going to cause you to lose half your fucking data of everything that you take a picture of today. You think you're going to get asked back? Not a prayer. This is the single most fundamental thing about being a digital tech that I can throw out to you right now is the importance of grabbing every possible shred of data that you can grab. It's not about trying to get something that looks like the end game. It is about maximizing your data. Are we clear on that part? Are there any questions about this? You can't believe how critical this is, and you can't believe that. I know that some of you have gotten images and you're struggling with your images. I have people show up. I see stuff that's 3, 4 stops underexposed. 4 stops underexposed, we get down to here. This is half the data, 3/4. This gets me from 3/4 to 80, we'll call it 90%. You get down here, whatever. You can see you're basing your data on 3%. Your image is based on 3% of the possible data. How in the hell do you expect to have a decent image? You can't. So then you would say to yourself, oh, wow, God, I thank God I'm learning this now, whatever, because I'm going to go into a studio and everybody there's going to know this shit. No, they don't. Some of the best photographers in the world don't know dick. They don't know anything about this stuff. They count on people like you to bail their asses out. That's a good thing. That means that there's a job and a place for you. Hi, I'm your ass bailer outer. So I just need to make sure that this is clear for everybody. Data is what we are talking about capturing here. And I don't care what it is you're doing. So the next thing that we are going to talk about, I'm actually going to show you guys, we're actually going to get away from this. We're going to go into the studio and actually look at some stuff, but I need to make sure that everybody is understanding why we went through all of this exercise. That because digital is a linear system that we are then having to scaffold into a logarithmic grid, data is what becomes the issue here. And that top stop, the top brightest stop of your exposure is the critical part. It is the part that everybody leaves behind, and it's half the data of your file. That's not like underexposing in film. If you underexpose in film, you're a stop off. That's 1/5 of a typical range of what we've talked about here. That's 20%. This is 50%. Huge. All right, we good on that part? Can you tell I get passionate about this? Shit drives me crazy. Okay. You need to hang with me for a second because I'm going to move this setup and rig into another room. So I am hoping I don't, if